Hello, thank you everybody. Thank you for inviting me in this workshop. I hope my audio can be heard well.
Yeah, it's good.
So,
thank you.
Okay, so I'm going to share my slides. Let me check. Let me see if it works. Not yet. Okay, let's see. Can you see my slides? No.
Yeah, we can see your slides.
They are full screen or
As
in
you
the editing mode? Just a moment, because I would like to share the presentation mode, okay?
Yeah.
Which is not this one. So let me check again. Stop. Okay. Okay. New combination. Okay, now you should see my slide in full screen. Is it correct?
Not yet. Okay, now yes.
Okay.
Thank you.
Thank you very much. I'm sorry. Okay, so I'm Luca Ferraro. I work as a computational scientist in the HPC department of Cineca in Italy. And basically, I'm in charge of the development and maintenance of simulation programs for seismic exploration and tools for post-processing in oil and gas. And I also participated in the EuroCC proof of concept programs, where I'm a software development for many other algorithms such as CFD and molecular dynamics. Okay, so during this talk, I was invited to talk about multi-GPU programming and multi-streaming programming. Okay, with CUDA. Most of the things that I'm going to show can be also quite easily applied to other low-level GPU programming models, such as AMD HIP or Intel OneAPI TPC, okay? But what I would like to stress here are the concept and the approach that you can make for multi-GPU programming. Okay, so we are going to have a little brief recap of what general purpose GPU programming model is. And then we are going to show how we can use asynchronous operations and streams to speed up your computations and to use all the resources of your compute node. And in general, also have a better efficiency of usage on single node and multi-node, okay? So let's start with a very brief recap. We have a node, a compute node that has a CPU and a GPU. We have several CPU sockets and maybe one or more GPU card devices. Okay, CPU are optimized for low latencies, accesses to cache datasets. So they are best used for serial operations or event-driven tasks. While, as we have already seen, GPUs are optimized for data parallel throughput computation. So, because they can handle thousands of threads efficiently. The general purpose GPU programming relates to the use of GPU computation to solve problems other than just graphics. So in order to use the GPU, we have to use CPU and GPU together and cooperate efficiently together. So they are seen as separate devices, both with separate memory space addresses. The GPU can be seen as an auxiliary coprocessor equipped with thousands of cores and high bandwidth memory. So they should work together to have best benefit and performances from your tasks. How can you do that? You already see from the other talk that an application can be ported to a GPU, keeping the serial parts of the program, keeping running on the CPU, on the host side, while the high parallel computation regions can be ported, can be executed on the GPU. Okay. In order to move the computation on the GPU, you have also to move data from the host side to the GPU global memory. So there are many ways to do that. You can do it explicitly using, for example, CUDA memcopy, or you can do that not explicitly, for example, relying on the unified virtual memory paradigms that are available, for example, in CUDA. So using, for example, CUDA malloc CUDA malloc managed, which will create a buffer on the host side with a counterpart on the GPU side, and data is transferred from the host side on the GPU side when it is needed on the device side, and back to the host side when the new data is needed on the host side. Okay. In general, this data movement can be the real bottleneck of performance when you have an application that is going to be ported to a GPU. Okay. So in this talk, I'm going to show you some techniques and approach which will easy and will, let's say, will lower the impact that these transfers will take place on your application. Okay. So let's talk about synchronous and asynchronous operation. The CUDA runtime, in general, offers functions which can be divided into two categories: blocking operations, that is also known as synchronous operation, which are operations calls to the API that returns the control to the host thread just after the execution is completed on the device. Example of blocking synchronous operation are, for example, all memory transfer performed with the CUDA memcopy. Memory allocations on the device are also blocking synchronous operations. Okay, so the control to the host, so the next instruction will be executed just after the completion of these operations on the device side. But the CUDA runtime API also provide non-blocking operations, which are also the counterpart of this previous blocking operation. Non-blocking asynchronous operations return the control to the host immediately, while the real task which has been invoked by the API is keeping on the device side. So while the device is still running the operation, the asynchronous operation, the host can keep on executing the other instruction of your code. Okay. For example, all CUDA kernel launches are asynchronous operation. Okay? Memory transfers of CUDA memcopy of data less than 64 kilobytes are asynchronous. Memory initialization on the device with the CUDA memset operation are asynchronous operations. And there are also memory copies from a buffer on the device and another buffer on the same device. All these CUDA memcopy inside the same GPU are asynchronous operations from the point of view of the host code, okay? And in general, we have also, as I said, counterpart asynchronous operation of known blocking synchronous operation API in CUDA. Why are asynchronous operations so important? Because using asynchronous functions allows us to perform concurrent execution of many transformation and operation on our node. For example, one concurrent execution is the execution of kernels, so computation on the device, while using computation on the CPU side, so on the host side. And this can be done in overlap. So you can use the GPU concurrently with the CPU, okay? Instead of using them serialized, okay? So computing all the kernel 1, kernel 2, kernel 3, and then CPU thread on the host, you can overlap the computation of some data on the host side while running the computation on the GPU side. But you can even do better. For example, you can overlap the execution of many kernels on your device. Or, for example, you can still overlap the execution of a kernel with data movement from the host side on the device side and back from the device side on the host side. This is very interesting because if you run a kernel on the GPU side and while using efficiently your communication buffer, you can hide data movement behind useful computation, okay? And this is the target of our talk for today. And since in general, the connection from the device to the host is a full duplex connection, you can also move data from the host to the device while you can retrieve data from the device to host concurrently, okay? Overlapping them. Okay, the first very simple example of concurrent execution of GPU with host work is represented into this sketch of CUDA C code. Okay, this is a pseudocode in general, but you can get an idea. As you can see, I start with a kernel launch. Here I can set the number of threads in a block and the number of blocks in my CUDA grid with some parameters. Remember that every kernel launch is an asynchronous call, so that when you launch this kernel, the execution begins on the device and the control comes back immediately to the host. So the host will begin the execution of CPU function immediately without waiting for the kernel to finish. Okay, so while the kernel is running on the GPU, the host can immediately launch the CPU function, which can be whatever. Okay, once you need the results from your device kernel, you need them on the host side, for example, because they must be copied from to disk, or can be, for example, transformed in another way. You can, in some way, synchronize insert a barrier in your code, and then, for example, make some copies from the device of your results onto the device. But here you can see that you can also use some APIs from CUDA that are used to synchronize the work between the host side and the device side. Okay, this CUDA device synchronize will stop the host execution until all the previous work enqueued on the device is completed. Okay, so this will behave as a barrier on the host side, and this barrier will be proceeded when the kernel, in this case, has completed its work. After this CUDA device synchronize, I can put other kernel, or I can, for example, retrieve data with a CUDA memcopy. And then I can also launch other useful work on the host or on the device. Okay. Now, in order to see how, so now we have seen how we can overlap computation on host and device, but in order to do the other stuff, so in order to overlap kernels or overlap kernels with the data movement, we have to talk about streams. What are streams? Streams can be viewed as queues of execution. So every GPU operation is implemented in CUDA using execution queues. Okay, so any operation that you invoke in your code is pushed into a queue, into a stream. Okay, and this operation will be executed only after all previous operations are completed. So it follows the first in, first out queue behavior. Okay, so if I say, please do this memcopy, then launch a kernel, then do this memcopy, all these three operations are pushed into a queue and will be executed in order. Okay. The CUDA runtime provides a default stream, a default queue, which is called also stream 0. And the default stream is always active. As soon as you initialize the CUDA environment, the default stream is ready to be used. So if you don't explicitly say, please enqueue this operation in some streams, all the operations are enqueued in the stream 0, okay? Which is the default stream, okay? All operations assigned to the default stream will be executed only after all other preceding operations assigned to other streams are completed. And another interesting property of the stream 0 is that any further operation assigned to other streams other than the stream 0 will begin only after all operations assigned to the default streams are completed. So I have some examples to clarify these two concepts. You have to imagine that you can define more streams, more queue. The stream 0 is already there from the CUDA initialization, okay? If you push operation on the CUDA stream, this operation cannot run concurrently with respect to other streams, okay? And the operation on the stream 0 will behave as, let's say, a barrier, okay, as a aligning point with respect to all other streams. So they will act as implicit synchronization barriers among other streams. Remember that all operations assigned to different stream other than stream 0 can be executed with any precedence with respect to the other. Okay, so let's make some examples. In the lower left part of my slide, I have declared two streams other than the default stream 0, which is already there. So in the left part, I will show the execution, let's say, the order in which I state some commands on the device. The color of the boxes show the stream to which I assign that particular command. So for example, command 1 in the gray will be assigned to stream 0. I choose to assign this command 1 to stream 0. Then after this command 1, I write command 1 and command 2 assigned to stream 1 because they are in gold, okay? Then I write, after this command 1 gold and command 2 gold, 3 other commands, which I will assign them to run on stream 2. In fact, they are assigned with a blue color, okay? And then I invoke another command, this is the command to assign to the stream 0. This is the order I write in my code. But how all these commands will execute on the device? As I said, since I started with command 1 on stream 0, no other command on other streams will begin until all command on stream 0 has finished. So the device stream execution will begin with this command 1 on stream 0. Okay? Now that the stream 0 has completed the command that I have assigned up to now follows a series of other commands to other streams. And since operations assigned to different streams can be executed with any precedence with respect to the other, for example, the device can choose to start with command 1 on stream 2, even if on the code it is written after the command 1 and 2 given on the stream 1, okay? Because streams 1 and stream 2 can run with any precedence with respect to each other, but inside each stream, operations will be maintained in the order assigned to each stream. So for example, the device now choose to start command 1 on the stream 2, then start command 1 on the stream 1, then interleave the command 2 on the stream 2, then run again command 2 on stream 1, then finish command 3 on stream 2. The command 2 on stream 0, the gray one, will not start until all precedent commands on other streams have completed. So, as you can see from this graph, command 1 on stream 0 and command 2 on stream 0 will act as barrier to synchronize the execution already pushed on other on other streams previously to this last command on stream 2. Okay, another example. Okay, now let's invert a little bit the order in the code. I add programs on my code. Okay, so for example, I have command 1 on stream 0, another command 1 on stream 1, another command 1 on stream 2, then again command 2 on stream 0. So as we already saw in the left example, this first set of command should be run concurrently with respect gold and blue. So I will not know if gold or blue will run, which of the two will be run first, but I am sure that they will not start until command 1 on stream 0 has completed, and I know for certain that command 2 stream 0 will not start until all the work on other stream has completed. So for example, here, this is an example of device execution. It will start with command 1 of stream 0, then it will take command 1 of stream 1, then command 1 on stream 2, and then again stream 0. Now that the command 2 on stream 0 has completed, the code follows with gold, blue, blue, okay? But the device can choose to pick them in any precedence, with maintaining the order inside each stream. So command 2 and command 3 will be executed with the right order, first command 2, then command 3, but they can be interleaved with other execution on other stream. For example, command 2 blue, command 2 gold, and then command 3 to end up. Okay. So this is the power of streams in CUDA. Stream 0 is used as a general synchronization point, as an orchestrator. Other streams can be chosen to enqueue operations, which can be in general run independently from other streams. Okay. I don't know if there are any questions on.
No, Luca, it's Özkan answering to the previous question.
Thank you, Özkan. Thank you. Okay, so I can go on. So this is an example, a concrete example of my previous slide. For example, here I declared two other streams, stream 1 and stream 2. I have to initialize this object with the CUDA stream create, stream 1, stream 2. Okay. Now I can choose to launch kernel 1 on different data, input 1 and input 2, on different stream. So for example, kernel 1 on stream 1 and kernel 1 with data in input 2 on stream 2. As you can see, you can choose in which stream other than the default stream, stream 0, you want to run a kernel, specifying this as the fourth argument of the configuration launch of the CUDA execution kernel syntax, which is this triple minus minor, 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 major, major, major syntax. Okay, this is a special syntax that Matti already showed you in his talk, during this talk. So the launch of kernel 1 on input 1 and the launch of kernel 1 on input 2, since they are enqueued on different streams other than the stream 0, can potentially be executed in overlap with respect to the other. Okay. Another example is the execution of kernel 1 and a different kernel, kernel 2, on these two streams, stream 1 and stream 2. Again, they are potentially overlap. They can be executed in overlap. But here, I also show you that I added here some other host operation function. call here. This is to show that all this stuff, launch of kernel 1 here, launch of kernel 1 here, launch of kernel 1 here, kernel 2 here, they are all asynchronous operations. So they are just enqueued into the streams. And while they are executing, the control keep on returning on the host side. So when it just enqueue these operations, it reach some other host operation immediately to be executed. So there is an overlap with the device and also starting already some other operation on the host side. Okay, so if you can see the on the bottom of my slide, the host execution point of view, if you sit on the host, you will see just kernel 1 launch on the stream 1, followed immediately from kernel 1 launch on stream 2, immediately followed by an enqueue of kernel 1 launch on stream 1, followed immediately by a launch of kernel 2 on stream 2. And I immediately reach this line while the execution of kernel 1 and kernel, for example, other on the stream, take place on the device side. But on the host side, I immediately reach the some other operation, host operation code, and I begin to run some other host operation on the host, while on the device, this operation takes place. Now, this is just an example. I don't know if some other host operation will finish earlier than the device side, okay? But whatever will last longer, you can see that there is still overlap between kernel execution between two streams and host execution on the host side. Here I wrote potentially overlap because they can be executed in parallel, of course, but they can run in parallel if there are enough resources to run them in parallel. So, for example, if you run this kernel and to run the kernel 1 requires all the streaming multiprocessor on the GPU device, they cannot run kernel 1 on stream 2 until they free up some resources. So, for example, if the device chooses to run with kernel 1 on stream 1, it begins to compute some of the work belonging to kernel 1. As soon as some streaming multiprocessor have completed their work on kernel 1 stream 1, they free up resources, and so they can begin to start working on the kernel 1 for the stream 2. And so here you can see a partial overlap, okay, on these two kernels. As the kernel 1 finishes its job, the kernel 1 on stream 2 keeps on running, and as soon as the stream multiprocessor resources will free up, other kernel can begin to run, and so on, okay? So I hope this picture of how the timeline of your device execution and host execution will take place during an asynchronous programming mode code, okay? As I said, when you have asynchronous concurrent execution, sooner or later you will come in need of synchronization, okay? You can use explicit synchronization with different refinements. For example, you can use CUDA device synchronize, which is a complete synchronization. It's a barrier on the host side, which will block the execution on the host side until all the work submitted to a device, whatever the streams, are all done. Okay, you can refine this synchronization point, for example, focusing on just one stream. So, for example, you can block the host code just with respect a set of operations submitted to a particular stream. Okay, so this is a barrier more selective. You can also use CUDA events that are simple flags that can be put in the code. In general, they are used to measure region of code, but they can also be used to, let's say, to spot some particular points in the code, and you can refine your explicit synchronization with respect to a stream and a particular point in the code. So you can say, please stop the host code until all the operation previously enqueued to that stream, previously enqueued of this event have completed. Okay, so you can be very picky on how you can control your synchronization on the host side. There are also other operations, other CUDA API calls that are implicit synchronization point. Okay, so for example, all the operation assigned to the default stream, as we already seen, behaves as implicit synchronization point with respect to the work assigned to other streams. For example, all other allocation of page lock memory, which we will see later, are implicit synchronization point. All other memory allocation on the device are implicit synchronization point, and so on. So you have to be aware of what is an explicit barrier and what is an implicit barrier that you put in your code with other CUDA call. Okay. Now we have talked about concurrent kernel execution. Now we have to explore how we can overlap kernel execution with data transfer. In order to make data transfer take place concurrently with kernels, you have to allocate the memory, the buffer of the data you want to move in a special way. You have to reserve this memory in a page locked fashion. This is also known as pinned memory. Pinned memory is a memory in which the pages they map to on the operating system, they are pinned in the sense that they cannot be moved by the operating system. For example, they cannot be swapped to disk or moved to make more use of other pages from other programs. Okay, so they are really pinned, and once they assign an address, they stay there until the end of the program or until you free up this pinned memory. Okay, so pinned memory is a very useful resource and should be let's say should be used with care in mind. Okay, how can you allocate pinned memory? You can use, for example, CUDA API, which explicitly allocate memory on the host memory in a pinned way using, for example, CUDA malloc host. The CUDA malloc host behaves very similarly to the classic malloc, to the standard C malloc. There is also a Fortran counterpart for also these CUDA APIs. Okay, but they will reserve memory in a page-locked way. If you allocate a buffer with CUDA malloc host, you have also to free it up with CUDA free host. Okay. If you already have an allocated buffer from a new operator or from a malloc or similar in your code, you can convert it into a pinned buffer using, for example, the API CUDA host register. This will turn host allocated memory into a page-locked memory. Okay, so once you have a buffer, a region allocated on page-locked memory, you can use this buffer, this region, to move data between the GPU, the device, and the host concurrently with, for example, kernel execution or host execution code. Okay? How can you move data in an asynchronous way since CUDA memcopy are blocking? The CUDA API provides you with also the CUDA memcopy async API. This function explicitly performs asynchronous data transfer between host and device memory. Okay? And you can also specify which stream you can use to do this data transfer. Okay? So this data transfer is an operation that will take place asynchronously on some stream defined, different from the zero, okay, and will take place concurrently with other operation of other streams or with the host execution. This is a pseudocode just to show you the idea. We have created two streams, stream A and stream B. Here with the CUDA malloc host, we allocate the buffer A and buffer B on the host side in a pinned page-locked memory fashion on the host side. We have, of course, a counterpart buffer A and buffer B on the device side, allocated with CUDA malloc. And here we can move data from the host side to the device side using the CUDA memcopy async API. And this will transfer the data from buffer A onto device buffer A using enqueued in the stream A, and concurrently, for example, transfer data from D buffer onto the H buffer B on another stream. And since the link is bidirectional, full duplex, this operation can be run concurrently, because while data from H buffer A transit from the host to the device, data from device D buffer B can transit back to H buffer B to the host side. Okay? This is very interesting. Why? Why are we using all these streams, these asynchronous operations? Because using them together can be combined in a chunking pipelining transformation. Let me get it into steps. Imagine you have a set of data you have to transform with a kernel on the GPU. So up to now, what you could have done, you can make a copy of the data from the host to the device. So it will take some time to process all this data, to move this data, this bunch of data from the host to the device side. Once this data is on the device, you can launch the kernel, because now the kernel can access the data on its global memory, and the kernel will take some time. And after the computation, the transformation is completed, you can move back this data from the device side to the host side. For example, you want to have a snapshot on the disk, okay, of this computation, okay? And you can call CUDA non-copy device to host, okay? So you move data up, you run your computation, and you move data back. Okay, since we are dealing with parallel transformation, this is the hypothesis, otherwise you cannot use GPU at all, okay? Because they run in parallel, okay? So since we are dealing with parallel transformation, we can think that these operations can be split in chunks. So for example, all this data can be split in 4 chunks, and I can move these chunks from the host to device in 4 different CUDA non-copy operations. Then I can launch 4 different instances of my kernel, one of the first chunk, one on the second chunk, one on the third chunk, one on the fourth chunk, and so on. And then retrieve data in 4 device to host CUDA non-copy operations, okay? And since we are dealing with parallel transformation, the order in which this computation is performed is irrelevant to the results. So we can rearrange this operation, thinking that we first transform all the first chunk of data. So move the first chunk, transform the first chunk, applying the kernel, and move back the first chunk. Operation completed on the first chunk. Now let's focus on the second chunk. We take the second chunk, we move it to kernel, to the device, we apply the kernel on the second chunk of data, we move them back, and so on. Okay? The result will be the same as in the first monolithic case, serial case, okay? Results will be unchanged. But since now you are aware of streams and you can also declare multi-streams, you can think that we can assign the first block of chunk, for example, to stream 1. So here we are declaring 4 streams, independent streams. We assign the transformation operation for the first chunk to stream 1. And we assign the transformation, the second part of the chunk, to stream 2. So the same for stream 3 on chunk 3, and stream 4 for chunk 4. Imagine the stream ordered along the y axis, okay? You will see that a moving data will take place on stream 1, and until the bus is busy, no other data movement host to device can take place because the bus is busy. So as soon as the stream 1 ends its host to device transfer and begins to run the kernel on the device, the bus is free. So stream 2 knows now that the bus is free and start its operation of host to device data movement of its chunk of data. Now, it cannot start its kernel until the streaming multiprocessors resources are busy with kernel 1 on the device. But as soon as kernel 1 or stream 1 streaming multiprocessor resources are freed up, the stream 2 can now launch its kernel. But during the kernel 2 on stream 2 is executing, transforming its data, the bus is now free. So stream 3 can take its third chunk of data and put them on the device with a host to device transfer, and stream 1 has the other side of the communication free, so it can begin with a device to host transfer. So as you can see, we have pipelined this operation into different streams, and we have saved time because we have compact this operation using, putting in overlap some operation that we previously have made serially, okay? And you can, this is just an example of the same things I have already shown. This is the code that declares 4 streams. You declare a buffer with the pinned memory on the host side, CUDA malloc host. And here we loop over the 4th stream. As you can see, the stream I of this operation will loop over the 4 streams declared in this code. So each stream will, in order, do these 3 operations. Move data from host to device asynchronously, call the kernel on this chunk of data, move back data. Since all these API are asynchronous, all these operations are enqueued into the streams, and the control of this loop will return immediately to the host. So here, the host can go on with other operation while all this stuff can take place pipelined on the device. Of course, you can have many levels of this concurrency. Here I showed you a 4-level concurrency, but we can add up many other streams and many other host concurrent operations, for example, using other multi-threaded paradigms for controlling the CPU side. Okay, so this is a very interesting technique. And this technique can be also used when you have a big chunk of data, a big portion of data that is bigger to be processed, which is bigger, for example, than the device global memory size. So if you have to deal with 80 or 100 gigabytes of data that in general can fit into the host memory of a compute node, but we still don't have GPUs with such an amount of global memory. So how can you deal with it? You simply split this huge amount of data to be processed into smaller chunks, and you pipeline this transfer bit by bit on the device, and you also spare time and you use efficiently your resources. Okay, we can also do better because all these concepts apply to one GPU. But if you have more than one device, GPU device on your node, you can also distribute this work on multiple GPUs. The CUDA runtime allows to control all GPU devices available on a computing node. For example, it provides you with API to get information on available CUDA devices, get their specifications such as compute capability, the global memory size, how many streaming multiprocessor units they have, and so on, so that you can, for example, make some runtime choices of some kernel launch details, for example, the block sizes, the chunk sizes, and so on. If you can refine very picky your choices with respect to the hardware that you actually have under the hood on the running compute node. Okay, and you can also select in which device you want to enqueue the operations. Okay, and you can also manage synchronization among streams running on different devices. Okay, let me remind you that when you specify a stream and you create a stream, the operation of creating a stream is attached to a device. So each device has its own streams. Okay, so if you want to use multiple devices with multiple streams, you have to declare streams for and initialize each streams for every device you want to use. Okay, so once you select a device, every operation that you are going, every CUDA operation that you are going to write in your code will be enqueued into that device. Okay, for example, let's see this pseudo code. The CUDA device count will return the number of available CUDA GPU devices present on the following, on the current compute node of the process. So once we have the number of GPUs, for example, 4 GPUs, okay, you can loop over the GPUs, the GPU ID that runs from 0 up to number of GPUs minus 1. Okay, so the IDs of the GPUs are numbers, integer numbers that goes from 0 up to the number of GPUs minus 1. So it is a C-like indexing. Okay, so if I loop over the available GPUs, I can say, hey, you, CUDA set device on GPU ID. So all the operations of all the CUDA calls that will follow this CUDA set device GPU ID will be enqueued on the device GPU ID number. Okay, so for example, in this loop, I will select GPU 0 and I launch kernel on GPU 0. Since kernel is an asynchronous operation, while the kernel is running on GPU 0, the loop control goes again on this 4, and the GPU ID now turns on to 1. I select CUDA set device 1, and then I select GPU 1 while the kernel on GPU 0 is running, and I launch this kernel on the GPU 1. And while it is running, I select GPU 2 and 3 and so on. Okay, all this is asynchronous. If you don't put any blocking operation, these orders will be given asynchronously to all your GPUs, and they will start processing your data concurrently on different devices. Okay, you have, of course, need to synchronize at some point. So you can, for example, select the device in another loop and say, please stop it, CUDA device synchronize, and you do that on all the 4 devices, for example, if you need to assure that every GPU has finished its work, okay, with this loop. Okay, I see there are a lot of questions. I hope to be clear enough, and I thank a lot my colleague Mati to answer these questions. Okay, now that you understand how you can get the number of GPUs and how you can select which GPUs to push command for, we can also expand the pipelining concept we showed just before to device chunking. So having multiple GPU programming can be used to speed up computation by chunking. So you can distribute num entries of data to be processed by a kernel on different GPUs, on all available GPUs. Of course, you have to track which data let's say, belong to different GPUs. So you have to take track of the starting index and end index of data that from the host side should be assigned to GPU 0, which other data should be assigned to GPU 1, and so on. Okay, so this is a very easy task, which can be, for example, solved with this simple loop. So for example, you have some data, you declare some streams, one stream on each GPU, for example. And here you set the device, you create a stream on that device. This is an array of stream, okay? So my index is for selecting a stream, and each stream will belong to a different device, because before I create a stream, I change the device here, okay? So each device will create one stream, okay? The device 0 will create a stream on GPU stream 0. The device 1 will create a stream on GPU stream 1, and so on, okay? Here I can compute the lower and upper index of the host data to be assigned on GPU 1, GPU 2, and GPU 3, and so on, okay? For example, choosing a chunk size, I can know where to start with every data on each GPU. You can also make here a mean to handle a reminder if this data is not, if you have reminders, I mean, okay. Then you can compute how many elements do you have to transform for each GPU. You can make a CUDA malloc on each GPU, which will host the data. And then you can make a loop selecting the device and assign the operation of copy host to device data, launch the kernel, copy back the data once the kernel has finished, looping on each device and assigning these operations, because they are asynchronous operations, to a stream that lives on each device. Okay? Okay. I have an example, a little demo for this later, so we can discuss and also make some answer and question time. Let me spend some words on device communication, okay? I have presented so far example in which each GPU takes its own data to be processed and then give it back to the host. There are many algorithms in which data on the GPU should be exchanged between GPUs. For example, let's think of finite difference transformation. For example, Laplace operator, in which you have you update each point of your grid with the neighbor data of the mid point. Okay, so when you subdivide this domain into subdomains assigned to different GPUs, you have allows borders that should be exchanged and updated between neighbors in order to have an updated solution of the cells that you are going to update. Okay, so you have to communicate this data that in principle resides on different devices. How can you manage to exchange this data between GPUs? The simpler and naive approach is the one that takes the data from the device, push it back on the host, and then from the host, put it on the right device, closing so the exchange. But this is tricky to code. It is also inefficient because this movement of data between the GPU and the host, and from the host to the other device, takes place spending, let's say, useful CPU cycles to manage this transfer. Okay, we can do better. CUDA, for example, CUDA SDK offers an API which lets you exchange data on a device, on the device global memory, onto another device global memory directly without passing through the memory of the host. Okay, this type of transfer, this direct transfer, is called peer-to-peer transfer. Okay, peer-to-peer transfer is often abbreviated as P2P. Okay, the peer-to-peer transfer is more efficient since it doesn't transfer data on the host global memory, but it directly transfer data from one global device to the other global memory device directly. But sometimes this peer-to-peer exchange is not available. In fact, before using this peer-to-peer API transfer, you have to query the availability of this peer-to-peer link between two GPUs. Okay, so for example, let's say we have GPU A and GPU B. This is GPU 0 and GPU 1. Okay, here we write the code from the point of view of GPU A. So we sit on GPU A, and I want to transfer data back and forth, for example, from and to the other GPU B. Okay, so the first thing I have to do is to ask my system if I have a direct link, a peer-to-peer link from me and my neighbor GPU B. How can I access to this? Using the CUDA device can access peer API. It will return a Boolean answer, yes, no. If it's yes, great, I have peer-to-peer access to that. If not, I can still write my code using the CUDA memcopy peer-to-peer memory copy API. But under the hood, behind the curtain, this communication will be anyway translated into a communication that will pass through the host memory, a host memory buffer, and then back to the GPU neighbor. All this stuff is performed by the CUDA driver, so you don't have to explicitly reserve host space for this communication to take place. Okay, it will be enabled automatically by the CUDA context and the driver. Okay, but querying this ability will give you an answer and a response with respect to the performance that you should expect from your code if or not this peer-to-peer communication can take place. Okay, so let's recap. If you want to exchange some data between two or more devices, you have to check if the peer-to-peer communication is enabled. If this is enabled, you activate this communication with CUDA device enable peer access with some destination point. And you can exchange CUDA memcopy peer from me, which I am GPU 0, to the other GPU B, and forth and back. Okay, if this peer-to-peer link is not available, these calls will be translated into a device to host copy and into a host to device copy, automatically handled. But performance will be more poor. Okay. Okay. During this workshop, we do not have time to cover all other applications of multi-GPU. For example, the CUDA API allows you to control just the GPUs belonging to one node, the node in which your current process is running. If you want to go beyond a single node, you want to use multiple nodes. Sorry, my cat is, okay. Multiple node, you have to rely on other programming paradigms such as MPI, PGAS, and so on, okay? Even in that case, you can control multiple GPU belonging to the process that runs on different nodes. If you want to run on other node, probably you want to exchange halos, for example, using MPI send receive. Okay, for those who knows MPI, the MPI send receive is just a communication between processes belonging to different nodes in general, which exchange a message. So I send data from a buffer to a process and I receive other data from another process into another buffer. That is send, receive, okay? And this is what happens when you have halo algorithm. You have to send the border, the left border of your computation to update to the neighbor and receive the right. And then receive from the right and give to the left, okay? This can be done, of course, with an explicit transfer device to host, synchronization. You make sure that the data that you want to send has been retrieved by your device. Then you make your MPI send to give your data to your neighbor. You will receive the data into another buffer. So when the MPI send receive call has completed, the data is sent, other data is received into a buffer, then you take this buffer and you will make a CUDA memcopy async to the device to update your halo, okay? And you will do this for each side of the communications. But sometimes you can have access to MPI implementation, which are CUDA aware. There are many MPI implementations which are CUDA aware. What does it mean? This means that the API of MPI can be used addressing directly the pointers, so the names of the buffers of the GPU side. So you don't need to explicitly move first data from device on the host and then make MPI call on the data on the host, but you can address the MPI send receive and other MPI calls directly using the pointers of the buffers that are in the global memory of the devices, okay? This depends on the MPI library that your environment, development environment is available on your machine, but as you can see, this will make your code much cleaner to read and to maintain. Okay, so there are many other things which can be taken into account, but this is just an idea of what you can read further to get deeper into this stuff. Okay, so wrapping up, we have seen how you can use a GPU to speed up a computation, moving data from the host to the device, launching a kernel and getting back the results. We have seen that splitting this GPU computation into smaller chunks and making use of stream and asynchronous operation, we can pipeline this operation and make an improvement over the general overall performance we can take onto our GPU porting code. And if you have also the benefit of you having a node, a compute node with several or multi GPU, we can apply the same stuff, the same pipelining stuff to multi-GPU, reducing the amount of work that each GPU should work with, and reducing again the amount of time in which your original computation can be transformed and completed. Okay, so that's all, folks. I hope you enjoyed this talk, and I'm available for question and answer. Here are some references. Of course, the online CUDA programming guide. Have also a look at the NVIDIA blog, where there are many interesting articles and covering a lot of stuff that we have presented during this this workshop. Regarding these techniques, multi-streaming and multi-GPU programming, I would like to point out these two presentations, CUDA Streams, Best Practice and Common Pitfall by Justin Lutjens. Is let's say an old but still very useful presentation that has been done during the GPU Technology Conference, and a more recent one on multi-GPU programming models by Jill Krause, which was given during the GPU Technology Conference of 2021. And there is also a very interesting example of this principle applied, for example, on the 2D and 3D finite difference Laplace or Jacobi iteration codes, which unfortunately we have not time to see together, and it is a little bit tricky code to comment. So I have chosen to show you a simpler example during this session. Okay, I have ended my presentation.
And thank you so much, Luca.
Martina, the demo, we will start the demo immediately, or do we want to?
Yeah, we have 10 minutes, so it could be better to start right now.
Okay.
And then finish in time.
In time, okay.
Thank you.
Sorry, I was I was a little bit late. Okay, so let me share my my terminal. In this short demo, I would like to show how we can apply the concept that I just showed you in my slides to a very simple operation. So let me okay. I will show you the solution of an exercise we generally assign to students during our Cineca courses. For example, if during September we will start with other courses, which are HPC courses, which are free, and so you can have a look at our offer. And we also make GPU programming courses, and we will see this material. They are held in English. And during these courses, we also present some, we give students some exercise. For example, this exercise is a very simple application of the stuff we just see. So we have to process two arrays. We have to combine the data of two arrays, array A, array B, into another output array, the array C, okay? If we have to do this in CUDA, we can port this code simply allocating a counterpart array A, B, and C on the device side using CUDA malloc, for example. Here are CUDA events just to measure the time and to measure the efficiency, the speed up that we gain moving this computation from the CPU side on the device side. So it is not very interesting. So for example, we copy the data from the host buffer A and host buffer B into the device buffer A and buffer B. So we have moved data. These are all blocking operation, as you can see, CUDA and copy. They are blocking operation, not asynchronous. There is a kernel launch. This is an asynchronous launch. So the control will come immediately back to the host, which is the immediately following instruction is a CUDA and copy. This CUDA and copy, if not explicited in other way, is given all these operations, the CUDA and copy, the kernel launch, the CUDA and copy, they are pushed into the default queue. That is the stream 0, okay? And they will be executed in order, okay? So there is no concurrency here. So the CUDA and copy, which will transfer the DC buffer onto the H host buffer, will take place just after the array, the kernel array function has completed, so that the DC buffer, which is the output of this kernel, is filled with the right data. Okay, so this will take just after this. And since this CUDA and copy is a blocking copy, this other operation here will not take place until the CUDA and copy is finished. And the CUDA and copy will not start until the kernel is finished, and so on, backward, okay? So this is a very basic example. If I run this, this is an example in which the kernel is basically a simple transformation. I take an element of the eData array, I multiply this data with an exponent of another data, another buffer, the J buffer, okay, which will make the argument of the exponent. So I combine these two input data into something else, and I store them on the output buffer, okay? I repeat this operation, for example, 100 times. This is useful to adjust the length of this kernel. Okay, so I can adjust how much the kernel will take to run these simple operations. Okay, with respect to the data movement. Okay, so the array to be computed is 2 gigabyte elements long. Okay, so we have 2 million elements to transform with this simple operation. Okay, now let me compile this example and run it. Okay, sorry. Okay, I have 2 million elements to be transformed, as you saw. This transformation has been decomposed into 8,192 blocks of threads, and each block of thread has 256 threads. Each thread will act on a different element of the array, okay? So once all the thread has executed their work, their kernel, the output will be put onto the D_C buffer, and then we take back it on the host. If we measure the total amount of time which is composed by the host to device movement of the two input array, the kernel launch and the device to host movement of the results on the device, this takes almost 3 milliseconds. The same computation, the same exactly computation performed of just one core by just one thread on the CPU takes 2 seconds and 0.8. Okay, so it is almost a 1000x improvement in performance. Okay, now let's evolve this exercise, which is all serialized, with stream in an asynchronous way. Here, I choose to use chunk of data of this size using 8 stream. Okay, so in order to pipeline my computation, remember that I have to put my original data on the host, not on standard buffer, but on pinned memory. So instead of using the standard C malloc, I use the CUDA malloc host allocation to allocate the initial data. I initialize my data, then I start my loop on the number of chunks I want to subdivide my original data. And for every chunk, with this function, I just compute the start and end index of my original host data to be processed for each chunk. Okay, I will push in my stream, my I stream, chunk stream, the movement of input data DA and DB. I launch my kernel in an asynchronous way on this stream, and I get back, the data. Okay. As you can see, there is an event record here and an event record start here. This event can be used to measure the lapse time. This is what I use to measure how much does it takes to run this code. If I run this code, this is just one GPU. This is the original run. If I run the second version with stream, here you see that I have almost a 4 times less execution using pipelining with stream. I can, of course, go further and try to use multiple GPUs. So now I can go beyond one GPU and use multi-GPU. Here I should anyway declare the streams for each GPU. So I will end up with, for example, an array of because of streams. Okay, because the first index select the GPU, And the second index select the many streams that I have activated on that particular GPU, okay? Malloc cost, starting with a pinned memory. I ask how many GPU I have available on my node. Then for each GPU I loop over the GPU, I allocate memory on that GPU to host, let's say, to host that particular data for each stream. Then I will loop over the GPUs and over the chunk of data that each GPU has to transform. Always with asynchronous memory movement, kernel function, and data retrievement. If I run this one, I should take also, again, better result. This is not the case, as you can see, with respect to the second, because, as I said, in this case, the length of the kernel is too short. Let's say the kernel is so short that it takes more to data movement to take place with respect to the kernel. But if I improve, for example, if I improve the length of the kernel, so instead of repeating this kernel 100 times, I repeat it 1000, and I do this both from the stream-only version and on the stream plus the multi-GPU version, you will see that I will have an improvement. One GPU, 6 milliseconds with streams. 4 GPUs with streams, 2 milliseconds. Okay. I have not time to show you the profiling, which would be also a nice thing, where you can really appreciate the overlap. Let's say this is the overlap of the execution, the blue kernel with the violet and green blocks of data movement. As you can see, they are all in overlap. And if I expand this, here you can see the 8 streams that I have used to pipeline the operation of data movement, kernel, and data retrievement. And they are interleaved between all the streams in the order that the device scheduler choose to be the best for the runtime of this runtime. But it ends up with this operation. If you see the exercise 3 with multi-GPU, you will see that there are several GPUs now, 1, 2, 3, 4, and all of this is used with the streaming. This is the smaller kernel part. This is the longer kernel part, and as you can see, there is almost full overlap on the, I would like to okay. There is almost total overlap of kernel execution blue line on the GPU 0 with the kernel execution blue line on GPU 1, GPU 2, and GPU 3. And all the other stuff, the green and the violet, are data movement and retrieval. So this is the maximum efficiency that you can achieve, for example, on this node with this task with 4 GPU and multiple stream. So I hope you enjoyed this talk. And if we share the slide, you have my email on the first slide, so you can contact me if you have other questions, and that's it. Thank you very much.
Thank you, Luca, for the great presentation and
Thank you.
demonstration. And as you said, considering the lack of time, if you have any questions, please contact the speakers by mail. And I wish to thank all the speakers for the interesting presentation and the participant for taking part in the workshop, and hoped it fulfilled your expectation. And as I wrote in the chat, you will be notified as soon as the slides and the recording are available on our website, EuroCC Access. And thank you again, and see you at the next workshop. Bye.
Bye. Bye-bye.
Thank you so much, Martina. Bye.